Hello kids, today we will be doing part 2 of our unit 3, which is force and motion, and right now we're on the fifth topic, which is pressure of solids. So let's get right into this. So when we talk about pressure, we want to understand how it feels for a mass to have its impact on something else, right? How much, let's just say if there's an object, let's just say it's a brick over here, what impact would it have if we just place it on some another object, right? So if you look at this, we have sponge over here, and on that sponge, if you put the brick in a vertical position, you will find that the sponge is actually pinched up more in the area which is under the effect of this weight, right? So it will have a weight which will act downward, right? And in this case, the same brick, if placed horizontally, will have the same weight, except now the area at which this weight is supposed to be acting has increased, right? So from here we can simply understand that it is not just the weight of the object, right? Over here, weight is the force which is acting downward, right? And if we look at this area, let's this area which is wider and over here which is smaller, we can say that pressure of a solid depends on two things. Number one, force, or what we say as weight in this case, right? And the area upon which it is acting, right? So if it means, let's just say if you have you know uh, an object which weighs about 1 kilogram, right? So its weight is going to be mass multiplied by its force of gravity, right? So that weight will be equal to 1 into 10 Newton, uh, you know, uh, uh, per kilogram, right? That's the gravitational force. So it will be 10 newtons, right? So that's the downward force of this object, right? This mass. But if we take the area to be 1 meter square, right? If it's a very wide area, then the pressure is going to be weight or force over area. That is going to be 10 newtons divided by 1 meter square, giving you 10 Newton per meter square, right? So that's the pressure that 1 kilogram is going to have on an area across 1 meter square, right? That means if I reduce the area, right? So let's just say I just made it pointier, right? It is now zero point 0.1 meter square instead of 1, right? I divided by 10 is the same mass over here, which is 1 kilogram, right? The weight is going to be the same. So in this case now, the pressure is going to be, let me change the color. In this case, the pressure is going to be a bit different, right? So the weight is the same, which is 10 newtons, which is the weight of this brick, right? But the area is now zero point 0.1 meter square, right? And that would result in 100 newtons per meter square. That means the pressure has increased, right? So why is it increased? Because of the area, right? So here we can safely say that pressure is inversely related, what we call as uh, indirect, right? Direct proportions and indirect proportions, right? Sorry. Okay. Yeah. Indirect proportions, right? Right. This is the indirect proportion to area of contact, right? So wherever this contact is done, right? For example, in this case of brick, this is the contact area, which I'm now highlighting with this pink color. So this is the area of contact. If the area of contact increases for the same amount of force or weight, then you will see an increase in pressure. In this case, this will have more pressure, right? And this will, on the contrary, will have less pressure, right? Less P. So this is going to be more P, right? On the contrary, even though the weight is the same, this is going to be the effect, right? So this is what it means to have pressure of solids, right? And it's a very small topic, so I'm not going to go much into the questions of this, but let's have a calculative question just for the sake of reinforcement. Let's just say if uh, a, a nail, right, a hammer nail is having an area of uh, let's just say 2 millimeters square, right? 2 uh, millimeter square, and is uh, applied a force, right? A force is applied. Let me just rephrase, my bad, please. Okay, if and a force of 10 Newton, which is the same as that of one brick, is applied, calculate pressure, right? How much pressure it would be uh, for this case, right? So P is equal to force divided by area. That is going to be 10 newtons, and it is going to be divided by 2 millimeters square, and this is going to be 5 Newton per millimeter squared. Now you might be thinking that this is a very small value compared to the previous one, right, where we had like 100 Newton, and then we also had 10 over here, but you need to look at the units. Millimeter squared is a very small area, right? So if I convert this into meter square, right, we do know that 1 meter square is equal to how many millimeters? 10 to the power 6 millimeter squares, right? So that's a huge difference. So if I put this over there, this is going to be an immensely big number, right? So it will turn out to be a very large number. So if I convert millimeters into this, so it is going to be 1 meter square divided by 10 to the power 6, right? That would be 1 millimeter square, right? And over here, this is since per meter square, it would be simply 5 divided by multiplied by 10 to the power 6, right? That would be in Newton per meter square. So the change in units will let you know how big this value was. So one brick is on 1 meter square, then 0.1 meter square, and over here this is going to be actually what we will call as 2 millimeter squares. 2 millimeter squares should be equal to 0.00002 meter square, and that sorry, I missed 1 0, right? So it is going to be 5 zeros and then a 2, right? So it is going to be 0.00002 meter square. So this is a very small number, right? So that is why the value turned out to be very large. So I wouldn't advise you to put a brake on a lane and put your hand underneath it, because that's going to be a very uh, you know painful injury over there, right? Because the pressure is going to be very high, even though it is just one brick which you can easily hold with your probably 2 to 3 fingers, right? You can easily lift it up, but that same brick, if just holding on to a nail, is going to be very dangerous for you, right? So moving on, this is about a little bit about pressure of solids. Very easy topic. It's more of a conceptual idea than complex mathematics. So it's a very simple mathematics that you can do. Nothing complicated over here. You just need to remember this formula. Pressure is equal to force, and force that we can take also as a weight, or the physically applied force, which is in this case over here, right? And divided by the area. The area can have different units. I've given you 2. Then you also have 3 unit areas, which I will write over here, right? Area over here can be expressed as, right, over here, area units that can come around would be meter square, right? Then we have centimeter square, then we have millimeter square, right? So it goes from higher to smaller and then higher to smaller, multiplying by over here it is going to be multiplied by 10,000, and over here this is going to be multiplied by 100. On the contrary, right, if we come back, it is going to be division, right, which we just did, right? and since it was already in the denominator, so that division actually got reversed and turned into a multiplier, right? So that is like basic mathematics over here. So you can simply convert these. Then other areas, these are metric, right? Metric, and then we have you can say American systems, right? American in American systems. Oh, that I don't know why my writing pad is slipping so much, right? American system uh, that uses inches, right? Inch square, and we also have feet squares, right? I will write the bigger one here so that it remains same, right? Feet square and then inch square. So over here there's another one to multiply the other way around, but I'm not going to advise you. Just remember that these two are also area, which is feet square, right, and an inch square. So it is going to be feet square or square feet, right? Both ways it is written, square feet, also written as sq dot ft dot, right, square feet. And then we also have square inch, right, also written as sq dot in, right? Or you can also write as inch square, or over here we can also have feet square, right, the symbol and the power 2. So this is about solid pressure, right? Now moving on to liquids. Now, when we talk about liquid pressure, we need to understand that liquids have a different mechanism since they can flow unlike solids. So, their pressure greatly depends on a few things. But the first thing that I would like to signify over here is that pressure, what we call as hydrostatic pressure, right? And why we call it hydrostatic pressure, as you can see this image, axial on direction, right? So if I apply pressure, let's say on this bellow system, which has several pores to it, and they are in different direction, but if I apply pressure on it, that pressure will be translated equally in all directions, right? So you will see water jet coming out in all these directions at same speed, right? There won't be any difference because this is applied, right? If I talk about natural pressure, then if I have this pressure holes or these pores over here at the same height, right? So it would be same if the level is same, and if the height is different, right, then you will find that different heights will have different pressure from low to high at the bottom, right? High speed. And why is that? Because there's more height to it, and that would increase the amount of pressure that the liquid is going to have. So over here we're clear about two things, right? That height, we can say liquid pressure, right? Liquid pressure depends on height. That's for sure, right? This what we can see from this experiment and this one, right? We can verify that at same height the pressure is same, at different height the pressure is different for the liquid column, right? And secondly, it's same in all directions, right? What we call as hydrostatic pressure, right? So that means if I go for a deep dive, so if my height is from the water surface, if this height is low, right, low depth, then the pressure is going to be low, as you can see with the small arrows. And if I take a deeper dive, then it is going to be high pressure, right? Deep dive will have more pressure. So, and you can feel that once you go into a swimming pool, that on the surface, barely below the surface, you don't feel much of the weight of the water, but as soon as you go deeper into the swimming pool, you would find that the pressure, the water is trying to crush you down, right? And that crushing force is due to the increased pressure of the liquid. So we are very well sure that the pressure of the liquid now depends, right? Pressure of a liquid, right? So we can define that it is going to be the weight of the water, right? How much water it is there. Obviously that depends on the height, but we'll still consider the weight, as we know that pressure is equal to weight or force divided by the area. Now in this case the area can be the area, right, over here of this cylinder, or it could be the area of these pores, how how many are there, the cumulative one. And in this case it could be these small pores, right, sum of all these, how much area is allowed for the pressure to come out, right. And area of the base will have the base pressure, right, what we call as hydrostatic pressure, or in this case the weight is going to be mg, right, mass into gravity, and area is A. So the pressure in the liquid can also be calculated from the same formula using this. Now over here we need to understand how much pressure is going to be there. We can use volume, right. So volume is equal to height multiplied by area, right. The height of this water column and the area of the water that is there. That means how wide we are, how much is the surface area, or the area that we pose to the water, right. And that we can simply subject to this from this area, that is going to be volume divided by h, right, area. And we can replace this area with this, so it would seem to have some dimension like this, right. Sorry, v divided by h, and this h is, since divided by the denominator, can go up, so it is going to be mgh divided by v, the volume of the water displaced and the height at which you are. So your body volume versus the height that you are in, that would define how much water will press you down, or how much pressure it is going to be there, right. So if you're possessing too much volume, then the pressure would be low and you'll be pushed up. Why? Because the water won't let you sink in. And if the height is increased, then obviously the pressure is going to increase a lot. If you go deeper, the pressure is going to be immense, right. So moving on, this was about liquid pressure, right. I'm not going to go into detail because the mathematical version is not supposed to be there in your work, right. I just gave you these ideas just to have, let you have a little bit of understanding how it actually works in mathematics. But you just need to remember this as a fact, right, that these two things are there, that liquid pressure depends on height and area, right. Height, and let's add area now, right, area, and it is same in all directions, right. So these 2 points are really important that you need to understand, which I've described. Other than that, you don't need that. Now let's move into gas pressure, right. So when we talk about gas pressure, right, what is gas pressure, right? It is the the amount of force exerted by these gas molecules or particles onto the walls of the container, right? So this wall of the container, whatever impact it is having from these gas particles, right, when they apply force on this, so it is also same in all directions, right. So the gas is applying same pressure in all directions. That is what we call as gas pressure, right. It's also same in all directions, but it is now on the contrary compressible. So let's just say if we had this jar in which there is a gas entrapped, I put some weight on it, right, and it has a certain area, so it will apply certain pressure on it. But if I apply more force to it, right, then I will compress the gas, I will push these molecules or particles closer to each other. That would definitely increase its pressure. So pressure over here is now related, directly related, or has a direct proportion with applied force, right. So if I apply more force, if I push the particles together, the force will be greater. As you can see, this arrow over here is smaller, blue one, and over here the red one, the gas pressure is higher, right. But over here we have the same number of same amount, right, same amount of gas, right. So we will deal with three cases. Applied force, so pressure is related, directly related to applied force, right. In this case, now in the second one, if we increase, right, increase the volume, right, increase, let's just say there was gas. Now this is fixed, right, this piston is fixed in both cases, so it cannot move up or down, right, unlike the first case in which the loading system was pressed down. In this case we have fixed the volume, right, a volume is fixed, right. In this case we reduce the volume from high to low, right, and that was for the same amount of gas. Now we increase the amount, of gas, and let's see what happens. You will see that this pressure gauge needle will move forward, right? So the pressure will increase. So if we increase the amount of gas, right, the gas pressure will increase, right? And why would it increase? Because now there are more particles in there to collide with the walls, hence increasing the pressure, right? That's what we said, that pressure is the amount of collision with the wall of the container, which these gas particles are doing. Now in third case, right, this I will name as effect of amount of gas, right? And over here, let me just draw a line. This was, uh, let me erase this. Since this is gas pressure now, so this is, sorry, gas, my bad, I write too fast. Gas pressure, right? This depends effect of volume decrease, right? If we decrease the volume or increase the applied force, then what will happen, right, for the same amount of gas? Now this is the third case, which is the last case, right? What will happen if uh, you know, the temperature is increased? So this is going to be effect of temperature, right? Effect of temperature. So increase in temperature will result in more energy or uh, collisions, right? Slash, right? Energy slash collisions, resulting in more pressure, right? In increase in pressure. So these are the three main factors for the increase of gas pressure. And what is gas pressure? It is the amount of collisions that the particles are having, the force that they exert on the wall of the container. So that can be increased by increasing the temperature, increasing the amount of gas for the same volume. Over here the pistons are also fixed, right? I will note it over here that these are also fixed, right, just like the second case. But in the first case the piston was not fixed, right? We will call this not fixed, right? The weight is not fixed, so we can increase or decrease this. If we reduce the pressure, the applied force, or reduce the increase the volume, then the collisions are going to be far less, because the particles will be moving away from one another, reducing the amount of pressure that is going to be there in the container. If we compress the gas, so it is going to have more collisions and more pressure, right? So now we move into the final topic, which is atmospheric pressure, right? What is atmospheric pressure? It is the amount of air pressure that we feel due to the air, sleeve, or you can say the atmosphere, the gases around us. That is the atmospheric pressure, which the atmosphere is always exerting upon us, right? So how much pressure is there? That starts, we do know that pressure for a column is inversely related to the area, but that is also related directly to the height, right? And pressure is related inversely to area, right? Whatever over area, that is like these two things, right? We need to worry about. So if the height, atmosphere has a huge height, so at the top of the atmosphere, at top, 0 ATM, right? 0 atmosphere pressure. And at sea level, max value, it will have the maximum value of 1 ATM, right? That is equal to 14.7 lbs, right, of pressure. We can say pounds per square inch, right? So that would be uh, per inch square, or that is also equal to uh, 14.5 psi, what we usually say 14.7 psi, right? So there are many ways we write this, but 14.5 is the most agreed upon value. On land, this is at sea level, right? A little higher. On land, since lands are a little higher than the sea level, so that's why the pressure is a bit low, but still quite close to the maximum value, right? So we can feel the maximum atmospheric pressure on land close to the actual value, but still it's a bit lower than the sea level, because sea is the lowest height you can get for atmosphere. Below that it's liquid, so we cannot talk about atmospheric pressure or gas pressure in liquids, right? So that's it for this unit. Now moving on to the last topic, which is I think the most fun topic, and it's more diagrammatic in nature. So what is diffusion, right? So diffusion is the process of particles, or one type of particles, spreading out in an other type of fluid, right? So one liquid spreads out into the other liquid, or one gas spreads out into another gas. Let's just say you have two containers, all right, separated like this, in which you have these pink particles, right, pink gas, and then we have another gas, which are these small particles, right? So once we remove this partition, right, once the partition is removed, what you will see that all these pink particles are now spread evenly uh, around the whole container, while the same is happening with these blue particles, right? They will also be spread out evenly. This distribution of gas is called diffusion, and it happens from higher concentration, where there's more of the molecules at one point. They will try to move outward into the places where there is low concentration. So the movement of particles from high to low concentration is called diffusion, right? Here's the definition for it, and you can see in the diagram that if we put a dye in liquid, it will slowly and slowly spread out, and the whole liquid will become slightly colored. But initially, as you can see over here, the dye is more concentrated, high concentration, so it will appear to be more dark in the beginning, but at the end it will become a wholesome light color, right? Because it is diffused evenly all across, which we call as the equilibrium state. So what are the factors that this diffusion depends on? There are two factors, right? So I will write factors, right? Factors for rate of diffusion. So this is one important question that I have over here, right? We'll get into this, but first we need to enlist two factors. First factor is temperature, and the second factor is mobility, right? Physical mobility, or physically if you shake or stir them, right? Stirring. So two things will affect, right? So over here, let's go through this question. What effect will increasing the temperature have at the rate of diffusion, right? The rate of diffusion will decrease, which is a wrong option, right? The rate of diffusion will decrease and then increase. That is again not possible. The rate of diffusion will increase. We'll discuss why is that so, but that's the correct one. And the rate of diffusion will increase and then decrease cannot possibly happen, because there is one trend in temperature, so it cannot have two trends in diffusion, right? The rate of diffusion will stay the same. That is also not possible. Now if you look at these this what is happening over here, let's just say if you put a dye in a liquid, you see diffusion or even distribution. The same thing happens when you're talking about gases. You can have fragrances. This is actually the nose, right? This is nose being drawn, and this is the fragrance of a cake piece which is coming to you, right? Or the coffee from the coffee mug, which we did one question in the workbook. So if we talk about that, so it depends on the rate of diffusion, right? If the temperature is greater, then the more particles, more energetic collisions are going to be there, more faster movement of particles will be there, so more diffusion will be there. And slower temperature, diffusion is going to be slower, right? So higher temperature will have more kinetic energy. That means faster diffusion, right? Now Another question that we did in the workbook was of this purple crystal, right? I had to find this exact image which could represent the question, right? Since the image is not there in the book. So if you put this, purple crystal in water, you would find that initially it has a very high concentration in the middle, right? Over the time, this pink color will distribute, and the whole thing will be, evenly distributed. Now over here, what I, have against this. Diagram is that this color should have been lighter, so I will lighten it out with a pink. If I could get a purple color, right? Let me just get a lighter purple color. Okay, that's much better. So this is how it will be distributed after a while, right? So uh, I'm changing the color to signify the importance of concentration gradient, right? So the color will lighten up over time, right? It was very dark initially, but then when the particles went farther away, it distributed evenly and it became light eventually, right? So this is how diffusion in liquid occurs, right? And it depends on two things. Number one is temperature, and number two is stirring, right? I can speed up this process. Sorry, it's too large. Just a minute. Okay, yeah, can be speeded up by shaking or stirring, what I am calling as mobility, that you physically shake this around, assisting in the diffusion, right? So you can do that, or you can increase the temperature to get this thing done, right? This is the end of this lecture. If this whole session, if you have any queries regarding this recording, please let me know. I'll help you better. Please check out the workbook solution is uploaded there. Compare your answers. If you have any ambiguity, please discuss. We have done most of these questions in the classroom. If you've have some of you were not able to make some complete graphs, so I went through the effort of drawing all these graphs neatly. So please try to ensure that your graphs are neat as the way I've drawn these, right? All you need is a triangle, the set square, and a clutch pencil, so that your pencil is sharp. Do not draw these graphs using a blunt pencil, because it looks very bad. I've explained these. You do not need to put these markers on these graph lines which I've made over here, that faster, stay, slower. I just made these to help you understand what is actually going over here, right? And these graphs need to be as clean as mine. Try to ensure you can do that just by having a clutch pencil and a razor and a set square. So please keep that. Also, you will not be allowed calculators in your assessment. So please avoid use of calculator. You will not be allowed one, right? Do mental maths. Do more practice of mental maths. I think that's essential even for me. Even I do that all the time. So we'll be seeing you for the assessment on Wednesday. Thank you.